afternoon. Today, our afternoon's talk will be given by Tatiana Smirnova-Nagnibeda from Genève University.
Thank you very much. Thanks a lot for the invitation. So I'm going to tell you about some research at the boundary of group theory, geometric group theory, and dynamical systems. And I'll try to give a colloquium-style talk, so I decided not to give too many definitions, but rather to concentrate on 3 examples. So there will be 3 examples of different groups related to different dynamical systems, and I'll try to give you some ideas. And the basic object from which everything starts is very simple. It's just the binary tree. So we will talk about automorphisms and actions of automorphisms of the binary tree. So I was thinking today that there was some mathematician who liked nature. Maybe he's been here, so he decided to call graphs without cycles trees, which is a very nice idea. But then there was a different mathematician who was the first to draw the binary tree, and he probably has never been outdoors. So because of him, the perverse tradition is to draw the binary tree with the root up and then the branches growing down. So obviously it's not like that in nature, but nonetheless that's how mathematicians draw this object, and that's how I'm going to do it. So we have the root, and then each vertex has 2 children, and this goes indefinitely like that, so it's an infinite object. It has infinitely many vertices. At each level you have 2 to the n, at the nth level you have 2 to the n vertices. Of course, the fact that it's binary, it's absolutely not essential. It can be any tree such that every vertex has the same number of children. And in fact, many of the things that I'm going to say is true even in a more general setting. I'm going to say later. Okay, so what's an automorphism of this object? So it should be an application from the tree to itself that takes vertices to vertices, edges to edges, and preserves adjacency, meaning that if 2 vertices were neighbors, then their images should also be neighbors. So it's just a normal automorphism of a graph. Now, if you think about that, you realize immediately that because the root has less neighbors than all the rest, it has to be preserved by any automorphism. And if the root is preserved, then all the vertices which are at distance 1 from the root have to remain at distance 1. The vertices at distance 2 have to remain at distance 2, and so on. So an automorphism of this object is in fact something which acts just by permuting vertices of a given level.
Is it infinite?
The tree is infinite. So you have Ln, that's the nth level of the tree, and n goes to infinity. So if you think about these automorphisms as acting by permutations of the vertices on the nth level for every n, then immediately you realize that such an action will have a natural extension to the boundary of the tree. So what's the boundary of the tree? We'll denote it, so this will be t, and this will be dt, the boundary of the tree. That's the set of infinite rays that start from the root and then go down indefinitely without making any backtracking. So a very natural way to view this object more algebraically is to introduce the alphabet with 2 letters 0 and 1. And this is the empty word. This is the word of 1 letter 0 and 1. This is the word of 2 letters 0, 0, 0, 0, 1, 1, 0, 1, 1, and so on. So this tree actually represents the language of all binary words, and the boundary of the tree represents infinite in one-sided binary words. Okay? Very well, so what's an example of an automorphism? So one example of an automorphism is just this switch, so let's call it epsilon. So this is something that just switches the 2 branches and then doesn't do anything below. This is an automorphism of the tree. But it's just very easy. It is just of order 2. If you do it twice, then you haven't done anything, and that's it. So let us try to find a more complicated example. For example, an automorphism of an infinite order. So for that, it would be useful for us to have some way to describe automorphisms. So let's think about this example. So So first of all, if we think about an automorphism, we should answer the question what it does at the first level, whether it switches the two branches or not. So this gives us a permutation belonging to the symmetric group of order 2. So either it switches the first two branches or it doesn't switch. Then, once we've decided that, we have to see what it does in the branches that grow from the first level. So we have the subtree which grows from the vertex 0, let's denote it by T0, and we have the subtree that grows from the vertex 1, let's denote it by T1. So we can look at our automorphism, what it does in T0 and what it does in T1. But now the essential idea of the whole theory of self-similar groups I'm going to tell you about is that this object, this subtree which grows from some vertex, it looks exactly the same as the whole tree. So when you restrict your automorphism to one branch, then you get again like an automorphism of the whole tree. So we get phi, which is an automorphism of the tree. Then you can write phi as sigma, which belongs to S2, or more generally SD if your tree is deregular. And then you have phi 0, phi 1. And phi 0 and phi 1 are again automorphisms of the tree. So we have a recursive way to describe our automorphisms. So now let me give you another example. So let us consider the automorphism which is given by the following recursive formula. We have epsilon, so epsilon belongs to S2 and it's not the identity element, so this is the switch, like this one. And then here we'll have 1 and A, sorry. So it means that we do the switch. Here we don't do anything, and here we apply A again. Okay? So how will this automorphism act? So if we try to draw its portrait, it's called portrait. So we'll have the switch here, and then we'll have the switch here, and the switch here, and the switch here, and so on. And elsewhere, it will act trivially. And this is an automorphism of the tree, and you can check that it will have an infinite order. And in fact, it generates a group, which is just the infinite cyclic group. So A is isomorphic to the group Z, and this group acts, so it is a subgroup of the automorphisms of the tree. And if you think how it acts, so let's look how A acts on words. So if A acts on the word, binary word, which starts with 0, what does it do? It changes the first letter, and then because the word started with 0, so we were here, so it doesn't do anything. So it just remains W. And then if we acted by A on a word which started with 1, then it changes the first letter, and here we apply A again. So do you recognize this dynamical system? If you think about the vertices of the binary tree as binary words, do you know what acts like that on binary words? So you change 0 to 1, you change 1 to 0, and then you have to do something else with what remains after you change 1 to 0. Sorry? I just didn't hear.
Addition by 1.
Addition by 1, exactly. So this is the very basic and very famous, well, let's say a dynamical system, which is just addition of 1 to a binary number. So it actually becomes a dynamical system once you extended it to the boundary of the tree. As I explained here, then you have also addition of 1 acting on the infinite binary sequences. So this is just the so-called odometer. So this is, it's called adding machine, or in other words, addition of 1 to binary words, and also called odometer, binary odometer. And so we have this group Z acting on T and also acting on the boundary of the tree. And typically this action is considered on the boundary with respect to the uniform measure. So this boundary of the binary tree is a very nice object. It has a natural topology. The base of topology is given by cylinder set. So you just fix the beginning and then you let it grow in any possible way with a fixed given beginning, and this would be a so-called cylinder, and those cylinders will form a basis of topology. And with this topology, this becomes a standard counter set, and it's also, so it's metrizable, it's compact, and it carries a natural uniform measure, where the measure of a cylinder is equal to 1/2 to the power length of the common beginning. So this is a very nice object, and you can consider topological dynamics or measurable dynamics, and so this would be an ergodic transformation with respect to this measure. Okay, so now, as in ergodic theory, you start with considering one transformation. So here we have this one transformation A. And then you would like maybe to consider more transformations and consider groups generated by more than one transformation. So what happens if I consider just some subgroup in the full group of automorphisms of the tree? Let's suppose that it's finitely generated, so we'll have some finite number of automorphisms that will generate our group. And we would like to write again, so some automorphism of this group as epsilon or some sigma, and then phi 0, phi 1 as here. Now the problem could be that this phi 0 and phi 1, they will again be automorphisms of the whole tree, but maybe they do not belong to the group anymore, right? Because here we now take not the whole automorphism group, but just restrict. So here we were lucky. Our projections were again expressed in terms of the same automorphism. So this is a nice property, right? It has to be called something. So groups which satisfy the property that phi 0 and phi 1 will again be in G are called self-similar with respect to this property that the branches of the tree represent the whole tree. So the tree is a self-similar object. So G is self-similar if phi 0, phi 1 equivalently phi restricted to any subtree growing from some vertex V belong again to G. And on the surface of it, this definition actually applies not to a group but to an action, and in fact it's true. So a self-similar group is a group which admits such an action on a regular tree. So I'm only going to talk about binary trees. You can, as I said, consider deregular trees. More generally, you can consider so-called spherically transitive trees such that every vertex of a given level have the same number of children. And this already is quite a general situation, because what is true is that any compact ultrametric space is asymmetric to the boundary of a spherically transitive tree. So if you understand well the actions by automorphisms on spherically transitive trees and their boundaries, then you actually understand quite a lot. So this is a very general setting, and regular trees is a very natural class inside those. Okay, so it turns out that this definition of a self-similar group is very natural, because it is equivalent to the group being generated by an automaton. So finitely generated G, a group of automorphisms of our tree T, is self-similar if and only if G is generated by the states of, and I'm going to write some words so that the statement is correct, but you don't really have to understand them, and I'm going to explain on the example. So generated by the states of a finite automaton. So what does it mean? Let me explain it on the example of the adding machine. So I'll draw you an automaton. So our group was just one generated, so we should have one non-trivial state in the automaton. And then what does an automaton do? So an automaton is actually a quadruple, so you have states, you have alphabet X, and you have two functions. The automaton is in a state at a given time. It reads the letter from the alphabet, and depending on the letter, it goes to some other state and also transforms the letter. So here, for example, let me rewrite. So what was the adding machine doing? So the adding machine was doing this. So this automaton should read letter 0 and return letter 1 and remain in the same state. So we write like this, and then it reads letter 1 and returns letter 0. When it reads letter 0, then it goes to the trivial state. And when it reads letter 1, then it goes to the same state A. Yeah, so it's like this. And the trivial state doesn't do anything. So this is the automaton, which it's actually just the equivalent description as the recursive definition of the generators. And the generators, except for the trivial state, will generate the group. So here this automaton generates just the infinite cyclic group. It is the group with one generator, and we've checked that it is of infinite order. So this is Z. Okay, so this is not a very illuminating example. Let us look at more interesting examples. So now I'm going to tell you about the three examples of interesting groups. Yeah, so why, maybe just a word about motivation, why I'm telling you about this. That's because the class of self-similar groups that I just defined contains lots of interesting examples. And it turns out that there have been a number of open conjectures in group theory, and counterexamples to all of those conjectures have been found in the class of self-similar groups. So at some point it became clear that the class as whole deserves to be studied because there are many interesting representatives inside this class. Okay. So you can find inside this class some classical examples. So for example, we have now an automaton with two non-trivial states. So we can write, I'll write also the recursive definition. So A0 is, so it changes, so it's epsilon and then A0, A1. And A1 doesn't change the letter, so it's just A0, A1. Like this. So it turns out that the group which is generated, so G generated by A0, A1 inside the automorphisms of the binary tree. This is the so-called Lamplighter group. Which was known algebraically since long time because it is just a semi-direct product of Z acting on infinite number of copies of Z2.
The automaton should be 0, 0, 0 and 1, 0. The ups.
Here it's, yeah, so here we have 0 to 1. This should be, what, 1 to... Okay, so A0 switches the letters, and A1 doesn't switch the letters. Like this, right? Yeah, thanks. So the Lamplighter group is the following structure. You have Z, Z, and then at each vertex of Z you have a lamp which can be either on or off, and you have a lamplighter which walks along Z, and at each steps it can either switch on or switch off the lamp. So the configurations of lamps are the elements of this group, and Z is the lamplighter which acts. So this is the group which acts, and the semi-direct product like this defines you a group which is easy to describe, but in fact it's not such a simple group. It's non-abelian, it's infinite, it's non-abelian, it's non-important, it's actually solvable of degree 2, and it has exponential growth. So if you measure number of elements at distance n from the identity element, then this number grows exponentially as n goes to infinity. So a solvable group of exponential growth. And this group was made prominent by the work of Grigorchuk and Kamenovich in the 80s, because they used those lamplighter groups to study random walks and to present first examples of amenable groups with non-trivial Poisson boundary, with non-trivial behavior of random walks at infinity. So this group still has trivial behavior at infinity for the random walk, but if you replace Z, not by Z squared, but by Z cubed, then this becomes already non-trivial from the random walk viewpoint. Okay, so maybe this is a good point to switch gears a little bit and to tell you about amenability, because this area turns out to be closely related to the study of amenability. So I assume that people here do not necessarily know what amenability is, right? Yeah, okay. So amenability, this was a notion introduced by John von Neumann in 1929, and he was...
Is there maybe a marker which is a tad more visible? Or?
Let's try. So he was trying to understand the Hausdorff-Banach-Tarski paradox. This paradox says that you can decompose a solid ball in R3 into a number of pieces, finite number of pieces, actually 5 pieces, and then reassemble these pieces just by acting on them by Euclidean motions, and then get 2 copies of the same ball. So the paradox is that, of course, it seems you cannot do it because the Euclidean motions preserve the volume and you double the volume, but the explanation is that the pieces into which you decompose your ball are not measurable, so they are very sparse, and so you can do it. And the mathematical explanation why you can do it is that the group of Euclidean motions of R3, of dimension 3 and higher, is non-amenable. So it admits this paradox, it admits this doubling effect. So the definition is that G, a group, it's actually a quite general definition, so it works for a topological group, but we will only be interested in countable groups, or the discrete groups. Is amenable if it doesn't admit a paradoxical decomposition, and what's a paradoxical decomposition? It's the way to write G as a union of m pieces that we call A and m pieces that we call B, such that there exists G1, Gn, H1, Hm in G, with G equal to the union of Gi, Ai, and also equal to the union of Hi, Bi. So you get this paradoxical decomposition. So you get 2 copies of G out of 1 copy of G just by rearranging the pieces. So it is immediately clear that you have groups like that. So just think about the free group. Free group is non-amenable. So free group is just all the freely reduced words in letters A and B. So we can draw them like as a four-regular tree. So you have the identity element here, A inverse, B inverse, A square, AB inverse, BA, B square, BA inverse, and so on. So that's the calligraph of the free group. And now what's the paradoxical decomposition? You can take all words which start with B, and then if you act on them, if you multiply this set by B inverse, you will get all the words except the identity. And then again, no, actually the identity also, because this one will go to the identity. And then again, if you take all the words that start with A and multiply by A inverse, you will get everything. Because after this letter, you have everything is possible.
From upper branch, when you multiply by inverse, you get 3 branches sidewise and up, but you don't get the down branch.
Ah, okay, maybe, yeah, you get everything except this branch. Yeah, you're right. But when you take the union with this one, then you get everything. So this, and this is a paradoxical decomposition. No, yeah, you're right. We need 2 pieces to reconstruct the whole with moving one of the pieces. Is a paradoxical decomposition. So what would be an example of an amenable group? So there is an obvious abstraction to having a paradoxical decomposition, and that's having an invariant mean. And so an amenable group is also a group which admits an invariant mean. So what's a mean? Well, I am kind of short of markers, I think. So a group G, M is an invariant mean on G if M is a finitely additive measure, additive positive measure on subsets of G.
Tatiana, I'm sorry. There is a...
there is a different marker. Yeah, thanks.
Yes.
On subsets of G, perfect. Such that M of G is equal to 1 and M of GA is equal to M of A, so it's invariant for any A subset of G and G in G. And obviously, if you have such a mean, and if you had a paradoxical decomposition, then you would just get 1 plus 1 is equal to 2, so this is a real paradox, so this doesn't work. So having such a mean is an abstraction to having a paradoxical decomposition, and in fact the converse is also true, so amenability is actually equivalent to having an invariant mean. And groups which are amenable, clearly you have finite groups, because you can just take the average on the group as the invariant mean. And then you can also see that Z has an invariant mean, so it's slightly less trivial, but you can take the intervals of bigger and bigger length and average over them, and in the limit you will get an invariant mean on Z. And so are there abelian groups? are also amenable, and groups obtained from final groups and abelian groups by elementary group operations like taking the direct product, taking the direct limit, and taking an extension. And for a long time there were two conjectures. First, people believed that maybe, well, it was a question rather, whether every non-amenable group contains the free group as a subgroup, firstly, and secondly, whether every amenable group could be obtained from finite groups and abelian groups by elementary operations. And both are wrong. So now we know that the class of amenable groups is much more complicated, and probably there is no simple algebraic description actually of this class. And so there are interesting groups which appeared as counterexamples to those conjectures. And so now I'm going to check the time. Okay, now I'm going to draw the automaton which defines a group which contradicts this second conjecture. So another example, it's called the first Grigorchuk group. So it was discovered by Rostislav Grigorchuk in 1980. It is a group of automorphisms of the binary tree generated by 4 automorphisms. A is just our switch, just switches the 2 branches and doesn't do anything else. And B, C, and D are recursively defined. So B is defined as AC, C is defined as AD, and D is defined as 1B. So let me draw the portrait of one of those generators. So for example B, so it doesn't do anything here at the root, but it does A here, which means that there is a switch here, and then it goes here and it does C, and C does switch here, so there will be epsilon here, and then here it will be a D, and D will do nothing here. And so it will continue like this. So you will have a distance 1 from the rightmost ray. You will have the sequence of epsilon, epsilon 1, epsilon, epsilon 1, and so on. And if you write C, then you will have epsilon 1, epsilon, epsilon 1, epsilon. This will be C, this is B, and D will be 1, epsilon, epsilon, 1, epsilon, epsilon, and so on. In fact, Grigorchuk defined this group not like this, not by automorphisms of the tree, but as measure-preserving transformations of the unit interval with the dyadics removed. And then you represent B, for example, as follows. You, on the first interval 1, 1/2, you exchange the 2 halves, and then from 1/2 to 1/4 you also exchange. And then from 1/4 to 1/8 you do nothing, and then you exchange, you do nothing, and so on. And this Lebesgue measure preserving transformation of the interval, this would be B, and C and D will be defined in the same way. So this is another way to define the same group. So there is one crucial feature of this group acting on the binary tree. So the action of G on T is contracting, and this means that if you look at, so you have your group G, and this is S, the generating set. So we have our group G and our generating set S, which are also the states of the automaton which defines the group. I'm not going to draw the automaton, but of course it can be drawn now that we have the recursive definition for the generators. So the length of every element G in the generators S is less or equal than 1/2. So here we'll take GV, length of G plus some constant C, where GV is the restriction of G to the tree growing from V. V is any vertex of the tree, and the length of G in S, that's the length of the minimal, so that's the standard length in group theory. You know, if you want to make a group a metric space, you fix a generating set and you measure the length of elements in this generating set, so you just measure what is the shortest word in the generators which represents this element. And this is a well-defined length of the group, and this is what makes the group a metric space. The length of the minimal, of the shortest word in generators S, representing the element G. And so this contracting property, and also the property that the action of the tree of this group is really non-trivial, in the sense that if you project actually the group to the subtree, you get the whole group G here and here. So you get that G actually contains the direct product of itself of finite index. So this property and this property, so which is called branch, guarantee and allowed to Grigorchuk to prove a very famous theorem that G has so-called intermediate growth. So there are many geometers here, and you know in geometry, if you have a compact manifold, you can consider its universal cover and measure the growth of the volume. And it's well known that for manifolds it can be either polynomial or exponential. And if it's polynomial or exponential for the manifold, then it's the same for its fundamental group. And so there was a question for a long time open whether there exist finitely generated groups which have growth in between polynomial and exponential, so strictly sub-exponential and strictly superpolynomial. And so this group, which is just defined on this small whiteboard, is the first example of a finitely generated group which has a growth strictly between polynomial and exponential. So obviously it's not a fundamental group of a Riemannian manifold, but nonetheless. So intermediate growth, actually the growth of G, it's bigger than x of n to the power 1/2 and less than x n alpha with alpha something, I don't know, I don't remember, but some number strictly less than 1. Okay. So one drawback is that G is not finitely presented, and it's still an open question whether there exists a finitely presented group with this property of intermediate growth. A priori it's possible, because not every finitely presented group is the fundamental group of a manifold. It's necessarily the fundamental group of a complex, but not necessarily of a manifold. So open. So G is not finitely presented. So it's described by a finite number of generators, but you cannot describe it with a finite number of relations between the generators. Open. If there exists a finitely presented group of intermediate growth. And I just wanted to mention that G is not finitely presented, but it still has a nice presentation, because I'm going to use this presentation in the second half. So just symbolically it can be described like this. So you have 4 generators, All of them are of order 2, as you could see from the portraits that I drew. It turns out that actually BCD, the product is equal to 1, so in fact the group is just generated by 3 elements, but it's convenient to write all 4 of them. And then you have the following infinite family of relations. Defined with the help of a permutation, sorry, not permutation, but a substitution, where tau is the following substitution. It takes A to ACA, B to D, D to C, and C to B. And so in the second half of my talk I'm going to explain how the subshift constructed from this substitution helps to deal with the group, but that will be a slightly different topic. So I still have a couple of minutes to define the third example. So my first example was the lamplighter group. The Eddy machine doesn't count. The second example is the Grigorchuk's group. And now the third example, it's called the Basilica group. So let me also draw, actually here I can do both, it just has 2 generators. And the automaton looks like this. We have the trivial state B, A. 1 goes to 0, 1 goes to 1, 0 goes to 1, 0 goes to 0, and here it's trivial. And this group is related to this mathematical object. So I'm going to write meanwhile. So this group, let's call it B. It's related to the complex polynomial f of z is equal to z squared minus 1, and oops. Let's project it here. Is it okay like this? Okay. So I just wanted to show you the picture because it explains the name. So it's called Basilica because so you have this complex polynomial z squared minus 1, and here is the pictorial representation of its Julia set. And this Julia set, people think, looks like the Basilica San Marco in Venice with its reflection in the water. So for this reason, this fractal is called Basilica fractal, and the group defined from this polynomial is called the Basilica group. So what's the relation between the complex polynomial and this automaton? It turns out that if you have a complex polynomial, or in fact post-critically finite, so with the finite orbits of critical points, either polynomial or any rational function with this property. So f, a post-critically finite rational function of C or in fact it can be defined also in a more general setting, but not important. Then we can look at its action on C minus orbits of critical points. Right? So it will be some partial self-covering. And then we can look at some point, so let's call this M. Let's take some point X in M and look at the tree of pre-images of this point under the action of F minus 1, minus 2, minus 3, and so on. So this is F minus 1 of X, and this is F minus 2 of X, and so on. So we will get, in this case, a binary tree because our polynomial is of degree 2. And now we have a natural action on this tree of the fundamental group of M. Because suppose we have some loop, so let's take some element of the fundamental group, so it's some loop based at X, so we'll take the fundamental group with the base point X. And take some element, some vertex at the nth level. There will be a unique lift of this loop by F to the n. It doesn't necessarily lift to a loop, but it will lift to some path in M, and so we will have some relation here. This element, I don't know, Z, will go to this Z prime by our gamma. So Z prime is the endpoint of the unique lift of gamma by F to the n, if this is at Z belongs to the nth level of the tree. And so we get the action pi 1 of M based at X acts by automorphisms on the tree of preimages. And of course this action is not necessarily faithful, because maybe there will be some loops which will only lift as loops. And so you have to quotient out by the kernel of the actions, because we only want faithful actions by automorphisms. We don't want any trivial actions. So pi 1 of M T quotient out by the kernel of this action is called the iterated monodromy group, EMG, of the function f, iterated monodromy group. And this interesting object was introduced by Volodya Nekrashevich around the year 2000. And this Basilica group, which is defined by this automaton or these two recursively written generators, is exactly the iterated monodromy group of the polynomial z square minus 1. So I suggest we take a break now, and then I will explain to you how the dynamics here is related to the group and how the substitutional dynamics is related to Grigorchuk's group in the second half. So Grigorchuk's group is amenable because it has sub-exponential growth. So amenability also can be understood. So I told you that amenability is equivalent to the existence of invariant means on the group. But there is also a different equivalent definition. And in fact, this property is known to satisfy literally hundreds of equivalent definitions. And one equivalent definition is that if you take cleverly chosen subsets in your group, and you consider the isochromatic inequality. So you look at the volume of the set with respect to the area of the boundary, then this ratio in an amenable group always goes to 0. So the infimum of dA over A subset of G, is equal to 0. They go to 0. So every group of sub-exponential growth is necessarily amenable, and so Grigorchuk's group is also amenable. But because it has superpolynomial growth, it can't be, no, actually because it has intermediate growth, no, sorry. No, sorry. Because it is an infinite, that's the easiest way, an infinite 2 group, so every element has finite order, has order 2 to the k, it can't be obtained from finite and abelian groups by elementary operations. And because it's finitely generated, because it's a finitely generated infinite 2 group. Actually, this is also a counterexample to a famous parasite conjecture which asked whether there exists a finitely generated infinite torsion group, but that was not the first example. Golat and Chaparaj constructed such groups in the 60s, so such groups were known, but this is still another example of an infinite finitely generated torsion group. But this was the first example of an amenable group which cannot be obtained by elementary operations from finite and abelian. And then once this example was constructed, people wondered, okay, but maybe amenable groups can be described as follows. Take all groups of sub-exponential growth and then apply elementary operations. And maybe this way, this is the way to get all amenable groups. And Basilica is a counterexample to that. So Basilica group is also amenable. And this, I will give a hint later. And it can't be obtained from groups of sub-exponential growth via elementary operations. And it has a self-exponential growth. Okay, so what should we do next? So now let me tell you about some graphs which are associated with those groups acting on trees, because they are very natural objects. Graphs. I think we probably know what's a Kelly graph. So if you have a group and a generating set, then to such a pair you associate naturally a graph, gamma, where the vertices are just elements of the group, and then edges are of the form one element and then other elements that you can get from it by multiplying by a generator. So for example, when I spoke about the free group, I drew a tree. So this was the Kelly graph of the free group with respect to the basis. When I talk about Z, I draw the line. So this is the Kelly graph of Z with respect to the cyclic generator. And you can do it every time when you have a group and some generators fixed. This is a natural way to view groups. And the metric with respect to this generating set is exactly the graph metric on the Kelly graph. So for example, when we talk about growth, we just can think about the growth of balls in the Kelly graph. Okay, so this is for the group itself, and But then if you have a group G and a set S, which acts on some, a generating set X, which acts on some set X, then you can consider Schreier graphs. Those are just generalizations of Kelly graphs of GSX. And then now vertices are elements of the set, and edges are again X and X on which you acted by an element of the generating set. And so when we have our binary tree and some group acting, so we established from the very beginning that any automorphism preserves levels. So we will have, so we have GS, and we will have some action here. I don't know, some graphs like this, labeled by generators. So this will be S1, S2, S1, S2, and so on. Okay, so we will get a family of graphs. This will be gamma 1. This is the Schreier graph of G S acting on L1, and gamma 2, the Schreier graph of G S L2, and so on, gamma M, and so on. And for the action of the boundary, if you take some boundary point, then you can consider its orbit under the action of G, and you will get gamma psi, where the vertex set will be G times psi S and G S, and the set here is the orbit of psi, so G times psi, infinite Schreier graph. And this is a whole family of graphs for every psi in dt. Okay, we have such a family of growing graphs. So the number of vertices of gamma n is 2 to the n. And it's kind of tempting to try to define some limit of this infinite family of finite graphs, also taking into account the fact that we have the infinite graphs somewhere there on the boundary. So far, people suggested 2 different ways to do it. So ways to pass to a limit in the sequence of graphs gamma n. So the first is the so-called scaling limit, and this is only possible when G is contracting, like Grigorchuk group or Basilica group. And in this case, the limit, so scaling limit of gamma n of the Basilica group, what do you think it is? It is exactly the Julia set of z squared minus 1. So what I showed you on the picture. And in the case of the Grigorchuk group, of gamma n of the Grigorchuk group, this is the interval 0, 1. So maybe I can show you the picture for the Basilica group because it looks nice. I'm sorry, I'm making you work. Yeah, so here on this picture, I drew the Schreier graphs for the action of the Basilica on the levels of the binary tree. So we have gamma 3, gamma 4, and gamma 5. So this is a four regular graph because there are 2 generators, and each time you have the generator and its inverse, right? As in the Kelly graph. You act by the generator, you act by the inverse. So those are 4 regular graphs. They grew bigger and bigger, 2 to the n vertices. And then this is what happens. So you could see that there were those cycles of length, of quadratic length. And then if you just represent them pictorially like that, cycles, then you see that in the limit you get this. But this can happen only because we have this contracting coefficient, and so you know what is the coefficient with which you have to rescale your graphs. Okay, now I'm sorry. Let us switch this off again. Oh, maybe sorry. No, not yet. Just because you like the pictures, I'm going to show you still another group that I'm not going to talk about. So you can also get this as the scaling limit of Schreier graphs of a group. So this is the Sierpinski triangle, and the Schreier graphs look like this, and this is the iterated monodromy group of this rational function, z square minus 16 over 27z. And this group can be actually defined as the group of moves of the Hanoi Tower game. So it is also very easy to explain to children if you're interested. And then you draw, this group acts on the ternary tree, 3 regular tree, rooted tree, and the Schreier graphs look like this. So this is the Schreier graph at level 3, and then in the limit you get the Sierpinski triangle. Okay, so now that's it for the moment. Okay, so this is one way to define the limits, but sometimes it can be good to have the limit even if the group is non-contracting, and so there is a more general way which comes from probability theory. So second way is called the Benyamini-Schramm limit. And it's actually completely general. Just when you have any sequence of finite graphs, gamma n, Benyamini and Schramm suggested a way to define their limit. So suppose your graphs were rooted. So suppose you had some special vertex in each graph. Then what you could do, you could define a local topology on the space of graphs. You could just look at balls centered at the root and see whether those balls look the same in the sequence as you go further and further. And then this defines the convergence. So we can look at the space of rooted graphs with local convergence. So convergence of stabilization of balls around the root. And now that's exactly the situation that we have in our case. Namely, if we take a boundary point psi and the graph gamma psi rooted at psi, then it will look exactly as the limit of Schreier graphs on the levels. So here there's something which are rooted at the points psi 1, psi 2, psi 3, and so on, which define the infinite ray. So psi is psi, is omega 1, omega 2, omega n, and so on. And we have here psi 2, and here we have psi n. So this belongs to L2, this belongs to Ln. And gamma psi rooted at psi is exactly the limit in G star of gamma n rooted at psi n. So this is easy to understand just from the construction. Now, what happens if you don't have a natural choice of a root? Then Benyamini and Schramm say, okay, then let us just choose a root uniformly at random and consider our graphs gamma n with this uniform measure, uniform distribution on the vertices or on the on the vertices of the graph, but this can be viewed as element of the space of rooted graphs. And then if you take this sequence of measures, you can go to a weak limit, and this is defined as the Benjamin-Schramm limit of this sequence. So the limit of a sequence of graphs is not a graph, but it's a probability distribution on the space of rooted graphs, or rather of isomorphism classes. Isomorphism classes of rooted graphs. So here it's much more concrete. So what happens here? Here we have a map. Let's call it big phi. From dt to g star. Every psi goes to gamma psi psi. Now on dt, so we can consider phi of dt the closure in G star. It will be some compact subspace. And then on dt we had the uniform measure, so it was a measure space. It was equipped with the uniform measure. So we can take the image of this measure by the map phi. So we'll take phi of dt closure and phi star of nu. So this will be a measure space, and this measure space is the Benjamin-Schramm limit of the sequence of graphs gamma n. And so I can show you the pictures. So in the case of the Basilica group, it turns out that this measure will be concentrated on infinite one-ended graphs that look like this. So they have quadratic growth, and here you have cycles of bigger and bigger radius. And so this corresponds to the typical points of the Julia set, which have typically just one. So if you take away one point, a typical point in the Julia set, you will get a one-connected neighborhood. So this corresponds to the fact that those graphs typically are one-ended. And in the case of the Grigorchuk group, we have the following graphs. So gamma 2 and gamma 3 are finite graphs, finite Schreier graphs, which correspond to the action of the second and third level of the tree. And then the infinite graphs typically look like this one, gamma psi. So it's just essentially a linear graph. And actually one can describe all graphs which are close relatives of the Grigorchuk group by describing graphs which have such Schreier graphs to the action on the boundary. Yeah, maybe I haven't said anything about the authorship of things I'm talking about. So there are many people who work in these areas since approximately the year 2000. So I mentioned Grigorchuk and Nekrashevich were essential to the development of the theory, and there are also Laurent Bartolzi, John Wilson, and I'm talking about joint works with Grigorchuk, Bondarenko, D'Angeli, Daniel Lenz, and also some of my PhD students. So there are a few papers that can be found on my webpage or the archive. Okay, so now I think I'm going to the last part of my talk. So what is the way? There are several ways one can study those limiting objects. And one way which I thought could be close in spirit to people doing geometry is spectral theory. So you know very well that if you have a geometric object, one way to understand the structure is to study the spectra of operators that you can define on this geometric object. And depending on the structure you have, there are various operators that you can define and so on. And so in combinatorics, people do the same. So if you have a graph, especially a graph with some additional structure like a Kernel graph or a Schreier graph, then you define Laplacians on these graphs or Markov operators which are related to random walks, and you study their spectra and you hope to say something about the original graph, original group or the action. And people were doing this in this context. And I'd like just to mention things that have been done in the 3 examples that we studied. I think we can switch off altogether now. So spectral theory. Okay, so if you have an infinite graph or just a graph, then you can associate with it the Laplace operator. Acting on the L2 space of the vertices, and it's essentially the average operator. So degree of delta of f at v is degree of v times f of v minus the sum of f of w, where w is a neighbor of v. So this is just the definition of the Laplace operator on a graph. Or people sometimes normalize it. So then delta is identity minus m, the Markov operator. And the Markov operator can be isotropic, where the random walk is just a simple random walk where you go in all directions with the same probability, or it can be anisotropic, which would correspond to attaching different probabilities to different directions of the random walk on gamma. And so you can be interested in the spectrum of gamma. So there is a conjecture. So people have studied spectra of groups, meaning spectra of the Kernel graphs, and there is a conjecture which is related to some deep conjectures in operator algebras, which says that if G is a torsion-free group, meaning that all elements have infinite order, then the spectrum of the Laplace operator on Kernel of G with respect to some generator S is a union of intervals. And the spectral measure should be just absolutely continuous with respect to the Lebesgue measure. And for a long time, the only examples that were known were like this. And in fact, it's quite complicated to compute the spectrum of a Kernel graph. So there are very few examples where it has been done. And there was a work by Grigorchuk and Zhuk in 2000 who used the automatic or self-similar representation to compute the spectrum of the Lamplighter group. So you remember this was my first example, and it is pure point. And yeah, so it's pure point, the measure is discrete, the spectral measure is discrete. So of course this group, it's not torsion free, it has torsion elements, but still it also contradicted some other conjecture about what kind of eigenvalues the spectrum of a group with torsion could contain. So it was a very interesting example of a computation of the spectrum. So how did they do that? The fact is that the action of the Lamplighter group on the binary tree and on the boundary turns out to be free. And so the Schreier graphs, the infinite Schreier graphs gamma psi, are actually almost all of them just the Kernel graphs of the group. And then they used the approximation of infinite Schreier graphs by finite Schreier graphs. And by computing the spectrum on the finite graphs, they were able to go to the limit and compute the spectrum on the limit. Okay, so this is one idea, use approximation. So the second idea is to use dynamical systems. So the same idea could be applied to Grigorchuk's group, and this helps to find the spectrum in the case of the simple random walk. So this has been done some time ago. But the substitutional dynamics gives us more. So second Grigorchuk's group. So here the theorem is the following. The spectrum of the Laplace operator on the infinite Schreier graph is a union of two intervals if and only if delta corresponds to the simple random walk, so it's isotropic. If not, the spectrum is pure point. And the spectral measure is singular with respect to the Lebesgue measure, and there is no eigenvalue. So there are two very different behavior for the Laplace operator on the same graph, depending on the distribution of the weights, and this is proved via substitution sigma or tau, which appeared in the presentation of the group. So there was this substitution: A goes to ACA, B goes to D, D goes to C, and C goes to B. And to this substitution, you can associate a subshift. So the shift T acting on the space of infinite words defined by the substitution. And it turns out that we have the following dynamical system. So there is a second theorem that says that we have G that acts on, so we have the action of G on this subshift, which is orbitally equivalent to the action of the shift itself. And there is also a factor of this action to the action of G on the space of its infinite Schreier graphs. Let me denote it as the Benjamini-Schramm limit of gamma n that I described above. And so, and this is 2 to 1. And so via this realization, one can actually lift the problem about the Laplace operator on the Schreier graphs to the problem about, now it's not Laplace operator anymore, but it's actually Schrödinger operator on this subshift. And we prove that the subshift is a subshift of low complexity, and then there is the whole theory of Schrödinger operators for the aperiodic order, and you can apply the results about the spectra and then deduce the results about the spectra of the Schreier graphs of the Grigorchuk group. And finally, the third example. So this part of work, I'm not a specialist in Schrödinger operators with aperiodic order, but we had a co-author, Daniel Lenz, who is a specialist in that, so that was a joint work. And then the third is Basilica group. So here we have the action of the Basilica group on its Benjamini-Schramm limit. So its Benjamini-Schramm limit was described explicitly in my joint work with my PhD student Michel Matter and two postdocs, D'Angeli and Donno. And we also have the action of Basilica on the Julia set of z square minus 1. And this action is actually conjugated to the action of the polynomial itself on its Julia set. And there is a question about various spectra here. So you have the spectrum of infinite Schreier graphs, and you have also the spectrum of Laplacian, which can be defined on the fractal, on the Julia set. And people who are specialists in spectral theory of fractals, so Luke Rogers and Alexander Tsekayev, wanted to compute the spectrum on the Julia set of the Basilica polynomial, and they were able to do it, but only for one Laplacian, which doesn't seem to be the correct one, so it's not conformally invariant. And there is another one which seems to be the most natural one, and for that one, analytical methods so far haven't given anything with respect to the spectrum, so do not allow to compute the spectrum. And so there is a hope maybe that one can use this part of the story to compute the spectrum, but the problem is that here the substitution is not, so to say, one-dimensional anymore. The subshift will not be one-dimensional because the Schreier graphs, as I showed you, they are not linear, they are quadratic. So one has to develop some higher dimensional theory of substitutional dynamics that could be applied here maybe with the, as a result of the computation of the Laplacian spectrum on the Julia set. Okay, I'll stop here. Thanks.